Hi, my name is Tachapon Saranurak. This is a joint work with Julia Chusoy and Parinya Chalermsuk. And this work is about binary search trees. So this is just a binary tree with a key on it. If this have key X, then everything on the left subtree is at most X, and everything on the right subtree has key at least X. And this is one example of binary search tree. We learn about BSTs in our undergrad studies, and it's like almost everything is solved. So what is still exciting about BSTs? So this is one example, perhaps the most exciting one. It is called dynamic optimality conjecture. So Bob Tarjan says that is the most interesting open problem in data structure and is his favorite open problem. Although it's not so important here to know what exactly it is, the conjectures say roughly the following, that there is a very simple algorithm called splay tree, which is the one approximate optimal dynamic BSTs. By dynamic, I mean allow rotation. And this is very exciting because if it's true, it would be like one of the most strongest beyond worst case guarantee for data structure problem. And it is very inspiring. There are so many papers published in top conference that is inspired, like really trying to solve this conjecture, but it still remains elusive until today. So there is an easier question, strictly easier question called optimal dynamic BSTs. It's the same problem basically. We just ask if there exists any constant approximate optimal dynamic BSTs. Instead of specifically talk about splay tree, just talk about any algorithm, can be offline actually. Okay, so this is easier. It's still wide open as well. And we will be focusing on this problem. There is also even easier problem called optimal static BST. This one is very classic problem now. You are given a access sequence X, you need to find a fixed binary search tree such that it has min cost for accessing X. It turns out that this is solved like long time ago by Knut and in linear time, approximately by Melhorn. Although this is solved long time ago, in contrast, when you allow rotation or dynamic BST, it's still wide open. And this is the necessary step for dynamic optimality conjecture. So we try to work on this problem. And very nicely, it turns out that to work on this problem, optimal dynamic BSTs, you don't need to know anything about binary search tree really, or any complicated data structure, pointers, rotations, nothing. Because you can just work on another problem called MinSat. It's a very clean problem, much easier to think about. And the reason is that Damon et al. Shows that these two problems are equivalent and it preserves approximation ratio up to constant. And this is what we care about anyway. So I will just tell you what is MinSat problem. It's a clean problem that is defined on a set of points on the plane. To define it, I need one definition, or two definition. The first is that we set that the 2 points P and Q. This pair is satisfied if there is another point in the rectangle defined by P and Q. Like here there is a yellow point, can be on the corner, on the border, or inside the rectangle. Or if P and Q are horizontally aligned or vertically aligned, then they are certified as well. This one is an example that they are not certified. Now, if we said that the set of points is certified if for every pair in the set, this pair is satisfied. So every pair here is satisfied. So the set, this set is satisfied, but this is not because of this pair. This pair is not satisfied. Okay, so in the MinSat problem, you are given a point set X in a grid, m by n grid, where m is the number of rows, n is the number of columns, and I will use m and n to denote the row and columns throughout the talk. We also know that the number of in each row there is only 1 point. Okay, so m is the size of X also. Yeah. And now our goal is to output Y, the set Y, such that when you union Y and X, this set is satisfied. And our goal is to add few points as possible. So we want to minimize the size of Y. That's the problem, really clean. And what is known about this problem, or equivalently, optimal dynamic BSTs, log n approximation is known, it's trivial, it's kind of an exercise. Then log n approximation is shown also by a breakthrough result by Demen, Hammond, Iacono, and Pratascu. Surprisingly, we don't know NP hardness, even in the exact case, although we believe that it should be because the variant of this problem is NP hard. But here we will focus on something in between. How about constant approximation and something below log n approximation? So this is what we show. Our result shows that if you want constant approximation, you can do something non-trivial. Sub-exponential time algorithm exists. We show this. And also, if you want anything below log n, we show a new barrier for any polynomial time algorithm using the known approach. The known approach is not gonna give you anything better than log n. All right, so let's talk about the positive result first. The full statement of this result is that for any k, you actually can get OK approximation for MinSat in this time, m, the number of rows, times something exponential in n. When k is a large constant, you get something like m times 2 to the n to the epsilon, where epsilon is any constant as small as you like. When k is log n, this expression simplified to polynomial, so which is known before. So this is a smooth trade-off from 1 to log n. Again, to remind you, you are given x, you want to output y such that they are satisfied, and the size of y is at most k times op, where x is basically the optimal solution of x. Okay. There are three main ideas. The first idea is to use dynamic programming. This gives an exact algorithm with quite slow time, like m times n to the n. It's quite simple, and I will skip it in this talk. And the next one is divide and conquer. This is a main idea. The idea is to decompose the problem into something smaller, into the smaller problem that has only root n columns and then recurs. So to tell you how it works, I need some concept. First, strip and compress instance. That is, suppose that you are given an instance x. If you look at a strip of columns here, you can define a strip instance x1, yeah, which is defined by restricting x only to this strip of columns. And you can forget the empty space. Okay. For other strips, you can define it similarly. And if the strips kind of partition all the points, then I can define another instance called compressed instance. This is obtained from x by collapsing each of the strips into one column. Like this 3 point become this 3 point in the same column. All right. And now the idea is really to just partition column into strips, each of size root n. So there will be root n many strips. And once you do this, observe that each of these xi and x tilde, they will have only root n columns. So they are smaller. So now if you use the dynamic programming that I mentioned before, instead of n to the n time, you can solve it using root n to the root n time. Is faster now. Okay. So you solve that optimally. And once you solve that, you want to get the solution for x. There are 3 steps for this. The first step is to kind of do a project each point in x into the border. So what I mean is, for each of the point, you project these 2 points like this. All right, very simple, into the border of the strip. Okay. Once you have done that, the next step is to get corresponding points from the red points. That is, for each one red point in the compressed instance, you add 2 points in the corresponding position, but to the 2 points on the border of the strips. The last step is to add a point from the yellow points inside the strip into something inside the strip again. Okay, I hope you get the idea. So now I claim that indeed this set is indeed a certified set. Why? Because if you look at any pair P and Q, if they are both inside the same strip like this, then there is the yellow point that certifies the rectangle. If you look at this rectangle, this yellow point will certify it. In the second case, if P and Q are from different strips, like maybe this point and this point, then you observe that there must be other light green point inside the rectangle. So that is good, it's certified. Otherwise, if both of P and Q are on the border like this, then there will be a red point that certifies the rectangle. So in all cases, every pair is certified. So we are good. And the cost is, we just count everything. The total number of yellow points will be exactly the total optimal solution here. So which is the sum of xi. The total number of red points will be 2 times of x tilde, and the light green point will be 2x. So that's the algorithm. So now we can conclude the analysis. The time we spend is basically the time when we recurse using dynamic programming, root n to the root n. The cost, I claim that these 3 terms will be still O of opt. And the reason is that I claim that basically each of the term here can be bound by opt. Why? Because the sum of opt of xi is at most opt of x. The reason is that for any solution for x, this solution gives a feasible solution for every xi simultaneously, and that's why this is true. Next, why opt of x tilde is at most opt of x. This is because once you compress your solution for x into, once you compress solution for x, you would get a feasible solution for x tilde. And next, the reason why x is at most opt. This is indeed true because if the point at row I and the point below at the row I minus 1, if they are not from the same columns, then in each row you need to add at least 1 point, right? So this you can assume by some preprocessing is a minor point and it's true. You can assume that. To all this together, you get that you get this running time root n to the root n, and the cost is O of opt. Now to get the full algorithm, the k-level algorithm, you basically just recurse this idea for k-1 levels, and then do dynamic programming at the last level. The running time would be something like this, because this is the number of columns at the bottommost level. However, the cost, if you use the same analysis I mentioned before, it will be something like 2 to the k. But this is not what we want. We want something like O of k times opt. But we can fix this using the last idea. It's a new decomposition lemma. So we argue quite kind of easily before that the yellow term and the red term, each of them is bound by opt. So if you sum them up, you would get a factor of 2. However, this new lemma says that you don't need this factor of 2. I will not tell you how to prove it. You can look at the paper. But once you have this, it will be enough already to just use the same analysis, but improved version, and you get the O of k times opt. The same algorithm would work. All right, so that is the idea of the first result. You have dynamic programming that is slow. You divide and conquer to speed up, and you have decomposition lemma for better cost analysis. Next, I talk about the low bound result is a barrier for log n approximation. Basically, we show a gap of log n factor between optimal cost and something called Wilber 1 bound. So I need to tell you what is Wilber 1 bound. Wilber 1 is some number, like given an instant x, you get a number just like opt of x. But it is defined based on something called reference tree. Reference tree is just any binary tree with n leaf. So 1 leaf per column, all right? And I will define this quantity called cross of Vx. This is basically the number of times that x cross the two strip of V. So let me tell you formally, like from the picture. So let's say that if this is a node V, then there are two strips of V associated with its two children. So this is the two strip of V. And we want to count how many times that the point in these two strips switch between the two strips. All right, so there are 3 crossing here. And that is how you get, so the cross of Vx for this node V is 3. For this node, there are 5 crossing. And for this node, only 1. Note that you don't care about point outside the strip, right? Outside the two strip. You only look at the point inside the two strip and you count the crossing. Okay. So Wilber with respect to t of x is just a summing of all this cross of Vx over all node V in t. So note that this quantity highly depends on t. If you change the tree, the quantity would change. And now definition of Wilber bound is basically you maximizing overall tree, Wilber t of x. Although there are exponentially many trees, you can observe that it is computable in polynomial time using dynamic programming, like a bottom-up way. This is easy to show. And now, all log n approximation algorithms are based on one inequalities, which is the following. First, Wilber bound is the lower bound of opt, and next, opt can be upper bound by Wilber bound based on with respect to T balance. So this is a balanced binary search tree. So opt is at most Wilber with respect to balance tree of x times log n. So just from this, you get a log n approximation polynomial time algorithm immediately. But can you improve this factor, log n? The answer is no. This is known long before, because it's known that for any fixed 3t, there is a sequence x depending on t, such that the cost, the opt of x is at least Wilber t x times log n. So you cannot improve this log n bound, but Wilber bound is actually maximizing over all trees, right? And you can so you can ask if the following is still true, that now you change, instead of one fixed tree, you maximize over all trees, and you hope that this is tight within constant factor. Is there any hope to prove something like this? Any hope to kind of extend the only known approach beyond log n? But sadly, the answer is no. This is because our second result, there is a single point set x such that opt of x is at least Wilber bound times something like log n. By the way, this bound is really improved to something tight, log n by LeConte and Weinstein. They are independent, but they use almost the same construction, but they give a tighter and nicer analysis actually. I really recommend reading theirs. So if you ask, can you get something like this beyond log n? Now the answer is no, you cannot using Wilber one bound. There are two steps to get this result. The first one is I show you how to construct a sequence x and say that opt is at least x times log n. On the other hand, Wilber bound will be at most or like O of x. So there is a gap of log n, and we would be done. Okay, so let's construct x. There are a few steps to do that. The first step is I define yi to be just a permutation of size log n, such that the opt of yi is not linear, it's strictly more than linear. Opt of yi is the size of yi times log yi. So you will basically get the overhead of log n. All right. And there are many known construction that yi exists, like yi can be a random permutation. All right. So that's the first step. And now the second step is, I call it y stack. Basically, you just stack y1, y2, y3, yn on top of each other n times. So you get this kind of picture. The number of rows now will be n log n rows. Okay, so there are n log n points in y stack and n log n rows. Okay, next, y shift is basically the same as y stack. However, each of the yi, the ith block, is right shift by I columns. So it looks like this. It's kind of the same as before, but the ith column is shift by I. The ith block is shift by I column. Okay. So now if you kind of zoom out, the picture looks kind of like this. That is, for each of these rows that I kind of compress it, it is really a one block of yi, and they are shifted by I columns at row I. So this is how it looks. Now the last step, finally, the sequence x is now the same thing as y shift, except that for each of yi, which is a block here, you make yi exponentially spaced in the following sense. That is, the first column is just like before, but the space between the ith column of yi and the I plus 1 point, there will be like a 2 to the I space between them, and this space exponentially increasing by a factor of 2. So that's why we say that these points are exponentially spaced, right? So each of the block, you just do this exponential spacing, and now the picture would look something like this. Each of this row actually is a block that looks like this. That's x. This is x. And observe that any solution for x would give you simultaneously a solution for every yi. So you get that of x is at least sum of yi. And that's why you get this log n overhead of x. So that's the first step. And now the last step. This is actually the most technical part of the paper to show that Wilber on this x is linear. In the paper, we actually have we don't show this bound. We have a log n factor here, but this can be removed. Actually, I will not prove this in full, but just to convey the key ideas, I will only sketch how to show that the Wilber of T balance of X is linear. All right. I hope that will already convey the key idea to you. And it's proof. And recall that Wilber bound is to sum over all crossing number. All right. Recall this of each node in the tree. So now let's look at one node in the tree, V, and look at the two strips here. And let me call IV to be this interval. Okay. Now what we need to count is the total number of crossing between the two strips. But note that you can see from the picture, right? Anything above this row, there cannot be any crossing, and also below this. Why? Because this part, the left strip here is empty and the right strip here is empty. So there is no point so there is no crossing possible. So the only crossing that is possible is actually only red points that I highlight here can participate in any crossing in this strip, which means that the total number of crossing is at most 2 times the red point, because you can have a zigzag in 2 directions. And the key technical part is to prove that this number of red points is linear in this interval. This will be true for T balance, but you can slightly adjust it for any other tree. But okay, but you can kind of, in this case, you kind of see by this picture that the total number of red points kind of will be proportional to the width of IV, this interval. Now, if you have this, you are done. Why? Because this Wilber bound with respect to this tree, you sum it up. This is, and now this is sum of the length of the interval, of the width of the interval, and this in total would be of size n log n, because the depth of this tree is log n. But n log n is the size of x, because there are only n log n rows here. right? So that's why it's linear. So that's it. I hope it conveys some picture, some idea to you from this picture. So that's now we are done. Let me conclude. The first result is to get a faster algorithm. We use dynamic programming, divide and conquer, and new decomposition lemma. The second result is to show that there is a gap between of log n between opt and Wilber bound. And that's why we cannot get something anything below log n approximation using the node approach. So that is the landscape of this MinSat problem for now, which begs the question, can you get anything better than log n in polynomial time? Or can you show the hardness, right? Again, even NP hardness for exact case is not known, but I believe this should be doable. So thanks a lot. By the way, there is one part that I skipped, and I want to tell you now. This is a part of one idea about how to use dynamic programming to get this exact algorithm with time n to the n in the bottom-up way. So let me tell you now how it works. So suppose that you have your solution up to, like you look at your instance up to row I-1, say, and you have your solution as well. Now look at the top point of each column. I can define a height profile pi. This is basically the order of height of these top points. So this is the first one, this is the second, and all of these are the third. So that's how you get 1, 2, 3, 3, 3. This is pi. Now consider the next row, that is the input on the ith row. So xi here. If you add this point to your solution, these yellow points, let me denote all of these points in row I by pi. Once you do that, then the top points change, right? It used to be no points here. Now you add this pi, the top point change, and the height profile change. You get pi prime, because now these are the lowest, and these are the second lowest. In this case, I say that pi prime extends pi via pi. And just look at another example, just to make it clear. In this example, these are the top points, all right? And you get the first here, second in the second and fourth columns, third and fourth here. Now you add some points pi in the ith row. It changes the height profile. So you extend this height profile to this height profile pi prime. Okay. The last concept to define the dynamic programming table is the following. We say that pi satisfies pi if for any pair p and q, where p is from pi and q is from the top point of pi, so the point that have red cycle around it. We say that this is satisfied if every pair like this is satisfied. Basically, we kind of forget all the points below, all right? And from this example, you have that pi does satisfy pi. And for this second example, this pi does not satisfy pi because of this pair. All right. So now I can define the dynamic programming table using this concept. I said that the optimal cost up to row I, if the height profile is pi prime, is obtained from optimal cost up to row I minus 1 when the high profile is pi. So this is the cost, and then we need to add this this new cost, which is basically the cost associated with this new yellow points. This pi minus 1. These are the number of yellow points. So we basically take this minimization over all pi and pi with this natural constraint, that is, first pi must contain xi. Right? Next, pi prime must extend pi via pi, and lastly, pi must satisfy pi. Yes, so that's are the three constraints, and what you need to return is to show that it's just an optimal cost up to row m, minimizing over all high profile. So almost by definition, you get the opt of x. And you would have also that the set that you choose according to this dynamic programming table would indeed be a satisfied point set because of this constraint. It's enough to make sure that each of pi satisfy pi from the previous row. And the time is basically the size of this dynamic programming table. You have m rows, and how many high profile can there be? N to the n. So that's it. So this is the end. Really, thanks so much.